In this lesson, we're going to be establishing two fundamental lemmas that we will continue to use throughout the term. And one thing about mathematics is that, yes, we are invested in proving major theorems, but oftentimes there are certain lemmas that get overlooked and are extremely powerful. And Bézout's lemma is one of those. And the other one is the linear combination lemma, which, while simple to state and also easy to prove, it's one that will be a recurring argument in our proofs as we go throughout the term, and as well as in future works in number theory. And so that's going to be the main plan for today, is talking about those, and then Blankinship's method, which is an algorithm that allows us to compute GCDs efficiently by using matrices with a process very reminiscent of row-reduced echelon form. So to get started, I want to actually harken back to linear algebra and pose some motivational questions to motivate where we're headed. So in linear algebra, we have vectors. So let's go. Suppose we have two vectors, v1 and v2, and we can even go ahead and take these to be the standard basis vectors for R2, 1, 0, and 0, 1. These turn out to be linearly independent, but we also define the span of v1 and v2, and that's the collection of all linear combinations. So we will have c1 v1 plus c2 v2, where now c1 and c2 are real numbers. And then if we look at this situation over here with the e1 and e2, then we will have that the span of c1 e1 plus c2 e2 for two scalars in the real numbers. This is simply the plane. And so here we have linear combinations, and we are going to now investigate the same process, but looking at the linear combination of numbers. And so let's make this precise. We can look at the linear combination of, say, 2 and 3. And this will be the collection of all numbers of this form. Let's go ahead and call this set S. And let's go ahead and look at this as 2 times m plus 3 times n. Now, there's going to be one major difference between how we approach this in linear algebra, where the scalars are allowed to be real numbers. Here, I'm going to restrict ourselves to only integers. So our scalars are now coming from the integers. And so just as an aside, this is part of what generalizes to what is known as module theory, which is a generalization of linear algebra, where scalars are allowed to be in Z, or more generally, in a ring. And so this terminology, we're looking at linear combinations, but now our scalars, m and n, that we're allowing over here, these are now integers. Module theory is a topic that is covered in commutative algebra and arose with Emmy Noether's work in generalizing the properties of the integers as well as the properties of vector spaces. Vector spaces are studied in the context of the real numbers, or more generally fields where you have inverses. With the real numbers, you take the number 2, it has 1/2 in it. Pi, 1 over pi. You have multiplicative inverses. And so all of this can generalize. And so this is just an aside of a different branch of mathematics that extends notions of abstract algebra. But for our purposes, we just care about this very nice, simple to state set. And let's go ahead and investigate what are the possible elements in here. So if we choose m and n, and we can go ahead and choose, say, 1, 1, then 2m plus 3n is just going to give us back 5. If we choose 0 and 1, we're going to get back 3. And so what I want you all to do now is just plug in a couple of points and make a conjecture as to what is S? Can we determine what S is? We know it's a subset of the integers, but can we make a conjecture as to what exactly is S as a subset of the integers? Can we conjecture what that is? Okay, so here we are. I put in a couple of points in, and we can see that we have 3, 2, 1, 0, 4, and -1. So it seems that we may be able to get every integer back. So as a conjecture, we could say S is equal to Z. And so that's something we want to prove. How can we go about showing this? In the language of the lesson on Monday, this is an instance of what is known as a Diophantine equation, because we could ask, and I'll define that more precisely on Monday, but for now, we could also ask the following question. So this question can be rephrased. So for what integers A does the equation 2x plus 3y equal A have a solution where x comma y are tuples of integers? And so that's one way that we can rephrase this question. Is we can think about it as, what is the set S? Or simply, what are the elements A appearing in the set S, but now phrased as a polynomial equation? So now let's consider the same question, but with two different numbers. What about if we chose 9 and 12? So can we conjecture what this new set S is going to be? Should we also expect that it's all the integers? Go ahead and plug in a couple values and check for yourself. So I've gone ahead and now included the corresponding quantities using the same m and n values we did in the previous example. And one thing that's striking from looking at these numbers over here is that they are all multiples of 3. So remember, 0 is divisible by every integer. And so we can conjecture S is equal to the collection of numbers of the form 3 times A, where A is in Z. Now, how do we know, should say conjecture, not equals. So we want to be able to prove statements like this, and Bézout's lemma is going to be one of the key ingredients for this. Another way of going about inspecting what's happening here is, why is 3 special in this situation? Well, for one, we can look at what is the greatest common factor of 9 and 12. 9 is 3 times 3, whereas 12 is 3 times 4. And so the common factor between them is 3. And as we will see, that is the key indicator for what is going to be the corresponding set S of the possible linear combinations of 9 and 12. And so the next lemma that we are going to prove is going to be a key step towards proving these statements, and actually very powerful. And what it states is the following. If we have integers d, m, and x and y, and we know that d divides x and d divides y, then d divides m times x plus n times y. And this is quite easy to prove, because we just have to go right through the definition. So let's apply the definition. So we know d divides x and d divides y. By definition, that means that there exists u and v integers such that x is equal to u d and y is equal to v times d. So now we look at mx, that if we look at mx plus ny, then substituting in the values for x and y, we get m u d plus n v d, which allows us to factor AD out. Mu plus NV, which implies that, by definition, D divides Mx plus Ny. Since what we have just shown is that D is a factor of Mx plus Ny, and now we have the proof of the linear combination lemma. And so this easy to prove lemma is going to be instrumental for our arguments going forward. And so from now on, I'm just going to refer to it as the linear combination lemma rather than the lemma 1.3.1. So our next definition is the concept of a greatest common divisor. So the greatest common divisor of two integers a and b, and we're going to assume that both of them are not equal to 0. So we're going to define the GCD of a and b to be the largest natural number d, such that d divides a and d divides b. Symbolically, we write d is equal to the GCD of a and b. And if the GCD is equal to 1, then we say they are relatively prime. And so we can see that in the examples that we looked at, we considered linear combinations of 2 and 3. But 2 and 3 are both prime numbers, and they're not the same, so the GCD there is 1. The GCD of 9 and 12, which was the other example, is equal to 3. And if we had, say, GCD of 21 and 33, then we can look at the factors. 21 is 7 times 3. 33 is 3 times 11. And so we can conclude from this that the GCD of 21 and 33 is 3, since we have the prime factorization of both numbers. But what if instead we wanted to compute the GCD of 426,930 with 123,945? And let's suppose further we want to do this by hand. Well, this is definitely out of the question. We're not going to go ahead and factor this. Yes, this one's even, and it has a 0 at the end, so we can say it's divisible by 5, and we know it's divisible by 2. This is divisible by 5, and then try to divide off and get the value. But we want to be lazy. That's really one of the motivations for number theory. It's like, here's these large numbers. Can we compute these things without having to do as much work as possible? Because this is too much work. And the answer is yes, we can solve it and by hand, and actually it's not so bad. There's an algorithm for this, and this is what is known as the Euclidean algorithm, also known as the division algorithm, as it is the name that's given to it in structures. But I want to emphasize that the division theorem is what we proved last lesson. The Euclidean algorithm is the algorithm which gives the GCD of two natural numbers, and we're going to go ahead and prove this in a bit. But let's go ahead and just talk about the algorithm without proof right now. And so what the algorithm says is, if we have natural numbers a and b, then let's go ahead and apply the division theorem. So the division theorem tells us that there exists unique numbers q1 and r1, such that r1 has the property that 0 is less than or equal to r1 is less than b. And so we can go ahead and write it this way. And now, here's the kicker. Once we write it in this form, if r1 is not equal to 0, we apply the division theorem again, but now to b and r1. And so we apply the division theorem to b and r1, and so now we have integers r1 and q2 and r2, where r2 satisfies the condition that 0 is less than or equal to r2, which is less than r1. And so now that's how b is equal to. And then we continue in this manner. We continue doing this each time. If r2 is not equal to 0, we continue. And then we get an r3. And if that r3 is not equal to 0, then we continue. And so the algorithm has the following form, which I am highlighting right now. So we will continue all the way until we finally get to an r sub n that is non-zero. and then the next step will give us back a zero quantity. But why does this terminate? Like, how are we guaranteed that this is going to actually terminate? That this algorithm is not going to go off to infinity and we just can do it over and over again? Well, the key thing is, by the way that this algorithm runs, we're always applying the division theorem each time if we have a non-zero quantity. And so in the setup, we start off with B, and we have an R1 that is less than B, but then we get an R2 that is less than R1. But these are always non-negative, so we always have that these are non-negative. And at every step, we go a smaller number. R4, and then so on and so forth. And so we are guaranteed to always end at some R sub n. So we can use this argument, essentially the ordering principle, there is a least element in this collection of R's, to conclude that there is some such an Rn. Now, the great thing about the Euclidean algorithm is that it actually gives back the GCD. So specifically, when we apply the algorithm to the example that we talked about with 426,930 and 123,945, we can go ahead and apply it. We apply the division theorem. So here we write 426,930 as our b times 3, and then we compute its remainder. Then we apply the division theorem once more, but now to the b and the remainder from the previous step. Apply the division theorem there. And then we get the q corresponding there is 2. The new remainder is this one here. And then we apply the division theorem once more, except that now we choose the 55,095 in this step as our A, and the remainder as our B. And so here we apply the division theorem once more, and we continue this process until we finally get back down to 30. But the key thing about the division theorem is that the last non-zero remainder, in this case 15, that's the GCD. And so it turns out that with this notation here, the GCD of A and B is equal to 15. And that is what we are about to prove, is that this in fact is the GCD. So let's move on. And in order to prove the Euclidean algorithm, the key lemma is this lemma 1.3.3, which tells us that if we have integers a, b, q, and r, such that a is equal to b, q plus r, then it turns out that the GCD of ab is equal to the GCD of b and r. So what does this mean? Just to give you some motivation of how this is going to be used in the final argument. What this is saying is that the GCD in this algorithm of a and b is the same as b and r1. But then when we go to the next step, we have that the GCD of b and r1 is the same as the GCD of r1 and r2. And then we continue this process. GCD of R2 and R3 is the same as the GCD of A and B. And so what's happening is, even though the numbers are changing at each step, we're going to have a descending chain of equalities of GCD. GCD of AB equals GCD of R1, R2, which is equal to, in turn, to GCD of R2, R3, GCD of R3, R4, all the way until we get to the very end. And so this lemma really is the key step to proving the Euclidean algorithm. Once we have this, the proof will follow automatically, essentially. So we're going to use a proof strategy for this. So the proof strategy is, so first off, we're going to go ahead and let D denote the GCD of A and B, and U to be the GCD of B and R. The strategy is to show that D is less than or equal to U, and also show that U is less than or equal to D. Both of these statements imply that then U is equal to D by the trichotomy axiom of the integers. Because now we have an integer D that is less than or equal to U, but also that U is less than or equal to D. But we know by trichotomy that two numbers are either equal, they're strictly less than, or strictly greater. You can't have an integer be both strictly less than and strictly greater. And so if we prove that both of these inequalities hold, this automatically implies that u is equal to d. Alright, so let's go ahead and show how this strategy works. So what we are going to do is use the equation that we're given. So from A equals BQ plus R, we deduce that U divides A by the linear combination lemma, which I'm abbreviating as LCL. Indeed, we know that U divides B and U divides R, since it is the GCD, and so now if we apply the linear combination lemma, it tells us that then U has to divide BQ plus R for any integers, in this case is any integers m and n, in our case is B and 1. And so as a consequence, we get that U divides A by the linear combination lemma. But now we use the following. Since D is the greatest common divisor of A and B, we have that U has to divide D. And then by 1.2.1, by lemma 1.2.1, we get U is less than or equal to D. And so that gives us one part of the strategy. For the opposite inequality, specifically D is less than or equal to U, we're going to rewrite the equation. So now observe that A equals to BQ plus R is the same, after subtracting, as A minus BQ equals R. In particular, we end up getting that D divides R by the linear combination lemma, because by definition D is the greatest common divisor of A and B. So now we are applying the same argument. We have A, we have B, we apply the linear combination lemma, and so now we have that D has to divide R. But using the same argument as in the first case, we now have that since U is the greatest common divisor of B and R, and now we have that D divides both B and R, we have that D divides U, since it's the greatest divisor. And then finally, lemma 1.2.1 tells us, implies that D is less than or equal to U. And then finally, by that trichotomy axiom, axiom of Z, it follows that D is equal to U, which concludes this proof, and we are done. Because now we have shown that both of these GCDs are the same. Alright, so let's go ahead and prove the Euclidean algorithm. So what we are going to show is that if we have two natural numbers A and B, if we perform the Euclidean algorithm to A and B, then R sub n, where R sub n is the last non-zero remainder outputted by the algorithm, is the greatest common divisor of A and B. And this is just going to be, so proof, just applying lemma 1.3.3. So we go with the notation of the algorithm as we have it on the lower right. So we're going to be using this notation here. So by the algorithm and lemma 1.3.3, we know that GCD of AB will have to be, is equal to the GCD of b and r1. But then when we get to b and r1, then we have this equation here. And so then the GCD of b and r1 is the same as the GCD of r1 and r2. So now we have that this is equal to the GCD of r1, comma r2. But if we continue in this manner, continuing in this manner gives us the following. That this is equal to the GCD of r sub n minus 1, comma r sub n. But r sub n is the last non-zero entry, because once we get to r sub n, the next entry is going to be rn, qn, and then the 0. So if we apply it once more, we're going to have r sub n, comma 0. But what is this equal to? And here's where we have to recall that every integer divides 0. So if we're looking at the greatest common divisor of 0 and rn, it's going to be r sub n. And now transitivity of equality tells us that the GCD of AB is equal to Rn, which is what we wanted to show, and we are done. And so we have now proven the Euclidean algorithm. And as we saw, the key step is this lemma. That was the key step. And now one thing I want to emphasize that we will not be covering in this course as much, but if you're interested in the computer science and computational aspects of number theory, is worth noting. This algorithm runs very fast in polynomial time specifically. So notice that we started off with 6-digit numbers. In this example, we had 426,000 something and then 123,000 something. And we got to the GCD in 6 steps, if we include the one with a 0 part over here. And so that's incredibly fast. And this is one thing on the computer side. You can compute GCDs with this algorithm extremely efficiently. So as an example, if you go to the textbook on page 162, actually, let me go ahead and add that picture here. So this is the examples mentioning on page 162. And so here, the text computes the GCD of two numbers, both are 25 digit long. And what it shows is that you can compute the GCD, namely 42, the answer to the universe, in 49 steps. And of course, by hand, this is a lot, but from a computational point of view, this is rather fast. And if you're interested, I highly encourage reading page 160 to 169 of the text, as they go in depth into polynomial time versus exponential time algorithms. And actually, they prove that if you're trying to compute the GCD of A and B, this is computed via the Euclidean algorithm in at most log base 2 of the product of A and B. And so there's an upper bound that can be proven for what are the most number of steps that you must take before computing the logarithm. The GCD of the two numbers. And so if you're interested, I highly recommend reading those 9 pages in the text. So now we get to our main result of this lesson, Bézout's lemma. Now, a historical note. Etienne Bézout, the statement that is referred to Bézout's lemma is not the one that we are proving. He's proved it in a more general setting, specifically in settings of polynomials. So essentially, think long division of polynomials. So he did that argument in 1799. Bézout's lemma, as is stated for the integers, dates back to Claude Messiriac, who proved it in 1624, hence the date on here. And as a comment of this general theme of generalizing, which we will see throughout the course, Emmy Noether in 1921 generalized it even further in the context of commutative rings. And so we will be experiencing a variation of that as we go further in the course, and we will actually be seeing the greatest common divisor in the setting of the Gaussian integers, which we discussed recently. So let's go ahead and prove this. Now, the proof of this is going to follow via the well ordering principle. So we're going to use the well ordering principle once more to show this statement. And what it says is that if we have any two integers a and b, and we let the GCD of a and b be d, we can always find integers x and y such that ax plus by equals d. So let's prove this. So first off, little comment over here, we have a and b are both integers. So I'm going to break this into two cases. Case 1, let a equals to b equal to 0. Now, when we define the GCD, we took it to be defined for one of the numbers being non-zero. Here we have two numbers that are 0. So we're going to take a convention that the GCD of 0, 0 is equal to 0. And so with this convention, we get the result automatically. Then we have that we can choose our integers x and y to just be 0 and 0, because then we have 0 times 0 equals 0 times 0, which is equal to 0. And so we have shown Bézout's lemma in the most easiest of cases. The good thing about that, doing it in this case approach, is that now we can assume that one of them is non-zero. So suppose one of a or b is non-zero. Define the set. Remember, we want to use well ordering principle, so that means we need a set. But how do we go about finding these sets? What's the intuition here? So a recurring theme that I want you to observe, as we have done with the well ordering principle, is we want to construct a set and use the well ordering principle on it. But how do we construct that set? Well, in this case, we have that we're fixing a and b, hence the subscripts. And what we want to show is this d. We want to show that that's the greatest common divisor. And the intuition is that we want to create a set that has all the positive linear combinations of a and b. And we want to then show that the least element in that set, via well ordering principle, is the GCD that we want. And so for that reason, this set, I'm going to define it as those collections of a times n, b times m, and I'm going to suppose that this here is always positive, such that n and m are integers. So by construction, because of the condition here that this is always a positive quantity, we get for free that this is a subset of the naturals. So we are one step closer to applying the well ordering principle. Next up is the set non-empty? The good news is we know that one of a or b is non-zero. So without loss of generality, suppose a is non-zero. Then a, or negative a, is in the set. Why is this true? Well, n and m are integers. So let's go by cases. If a was positive, we can take n to equal 1 and m to be 0. So we have a times 1. A is assumed to be positive, so this is in that set. And ta-da! We have a is in the set as a comma b. If it were not the case that a was positive, because it is non-zero, it must be negative. But then negative a is positive. And then we come back over here. We can choose n to be negative 1, so we have a negative a. Choose n to be equal to 0. So we have negative a plus 0, so just negative a. But that's positive, so it is in the set s sub a comma b. So therefore, we have that this is non-empty. And then by well ordering principle, there exists a u in s sub a comma b that is a least element. And so we have this here. Next, what we are going to do now is use the definition. U is in the set S A comma B. So in particular, there exists x and y in Z such that u is equal to a x plus by. And so here we just use the definition of what it means to be in the set. We know that the GCD of A and B is D. And so D divides A, D divides B, so the linear combination lemma tells us that D divides U. By the linear combination lemma, we have that D divides U, and thus D is less than or equal to U. So now it suffices to show that U is less than or equal to D, so that we can use the trichotomy axiom of the integers. And so that's what we are going to do now. So now let's go ahead and apply the division theorem to U and A. So by the division theorem, applied to U and A, we have that there exists Q and R in Z such that A is equal to U times Q plus R with 0 less than or equal to R less than U. And so we have this here. Now what I want us to keep in mind is that we know what U is. U is equal to AX plus BY. So let's go and use that. So let's first write this in the following way. Let's write R is equal to A minus U times Q. Now substitute in for U. So we have A minus U, which is AX plus BY, times Q. Expand this. We have A minus AXQ minus BYQ. Collect like terms. We have A times 1 minus XQ minus BYQ. And so we have this here. And here's the thing. It's like, this is the clever aspect of this proof. There's a red herring that I want to emphasize. We have been working with these GCD arguments, so it's maybe the case that we look at this A and B and say, oh, we have by the linear combination lemma, D divides A and B, so therefore D divides R. But that's actually not going to lead us to what we want. Instead, remember, we have the well ordering principle. If we're using well ordering, we want to essentially get something along the lines of this set that we have. And instead of looking at the linear combination lemma, where D divides R, we instead want to see that what we actually have is 1 minus xq and yq here are elements that we can choose for n and m. So in other words, if R is positive, if R is greater than 0, then R is in S of A, comma B. And so this is what we want to use, is this aspect where we have written this in the way that the elements in the set of S sub A, comma B are. And so we have R is in S sub A, comma B. R is positive. But what's the problem with that? Well, let's go back to how we set up the argument. We got R from the division theorem. And the division theorem told us, by construction of it, that R is less than U. This is a big problem. Because now we have a contradiction of minimality. So this contradicts the minimality of U in S sub A comma B, therefore R must be 0. So now that we have that R must be 0, let's go back to where R was defined. A is equal to U times Q. So in other words, we have now shown, I'm going to put this in a box over here. So this shows that A is equal to U times Q. And now what I want you all to do is apply the division theorem to B and U. So in other words, you're going to have B is equal to U times some Q prime plus R prime, where Q prime, R prime are integers, and by the division theorem we have that R prime is less than B. And what you're going to show is that the same argument that we just did will show that U is equal to B is equal to U times Q prime, because you will deduce that R prime is equal to 0. Let me give it some more space here. Alright, so now I have resized everything. So if you apply the division theorem, so now you can show, let's start again over here. So now show, so I leave this for you all to just practice with this argument. Now show that then B is equal to U times Q prime. But then, once you show that, we are essentially done, because now we have A is equal to U times Q, and B is equal to U times Q prime. So therefore, U divides both A and B, and so in particular U divides B, the greatest common divisor of A and B. So we end up getting that U is less than or equal to D. But that's what we wanted to show. Since we already showed that D was less than or equal to U, we needed to show that U is less than or equal to D. And so thus U is less than or equal to D, and this completes the proof, and so QED. And so now we are done with this argument. And a nice consequence of Bézout's lemma is the following. If A and B are relatively prime integers, then there exist integers x and y such that ax plus by is equal to 1. And so this is just automatic, because if the GCD is 1, so if the GCD is 1, then Bézout's lemma tells us that there are integers x and y, so that ax plus by is equal to 1. And so we are done with that statement. Now, what we want to move on towards now, actually, let me, before going there. Bézout's lemma, as it's done, if we go back to the proof, this is an example of a proof that is non-constructive. It tells us that, yes, if we have two natural numbers a and b, we can find integers x and y such that ax plus by equals d. But how do we find the integers x and y? How do we find them? How do we construct them? Because in the proof, we end up getting it, but by arguing through the well-ordering principle. We constructed this set and we found the least element. And then we showed that that least element has to be the GCD, and so by construction, there are some n and m. And that's what we did over here. We said, oh, u is equal to ax plus by. But we never found what the x and y were, because we knew that the set was non-empty. And so we knew that we can find the least element, and so we had those x and y for free, which works to prove the statement, but doesn't give us any means of finding the actual values for x and y given two integers a and b. And that leads us to Blankinship's method. So Blankinship's method is actually rather recent. It was just, published in 1963. The textbook offers an alternate way of computing the x and y for the GCD, and so I leave that to you to read. This is referred as Euclid's Royal Road in the textbook, method 5.2.2. And so instead I'm going to use Blankinship's method, which is reminiscent of row-reduced echelon form in linear algebra. And so here's the statement. Suppose a and b are positive integers, and we're going to always assume that a is greater than b. And then we're going to write the matrix M, the identity matrix in the 2x2 right here, and then we're going to write A and B. And so what it says is that we can find a 2x3 matrix where the entries are going to be x, y, u, v, and then d, 0. And x, y, u, v are integers, d is a natural number. And once we get this matrix of this form, once we have that 0 in that lower right-hand side, this is going to be the matrix we want. Because what we end up getting is that then that D will be the GCD, and we have AX plus BY equals D. So let's see how this works. We're going to start off with 35 and 15. So we're going to start off with our matrix. And so we're going to have 1, 0, 0, 1, and then 35 and 15. And now Blankinship's method, what it's getting at is that we want to get to n via the following process. We want to add multiples of one row to another and interchange rows. And so it's much more restrictive than row-reduced echelon form. So we can only add multiples of one row to the other and interchange. Now we know that what we want to do is get to that 0 on the lower right. So, with that in mind, let's go ahead and multiply the first row by 2. The second row by 2. So let's do 2, row 2, actually negative, sorry. And then we're going to add this to row 1 and replace row 1 with that. So that will give us, the 1 stays the same since we're going to be doing, in this notation, negative 2 times 0 plus 1. But now here we'll have negative 2 plus 0, so we're going to have a negative 2 in this entry. And then negative 2 times 15 is negative 30, and then plus 35 we get positive 5. And so now we have 0, 1, and 15. And so we have that. So we brought down that 5 down. And now we're going to go ahead and cancel off the 15 by multiplying the 5 by negative 3. So we can cancel off that 15. So I'm going to write it symbolically as we're multiplying negative 3 to row 1, adding it to row 2, and then replacing row 2 with that. So now row 1 stays the same, so 1 minus 2, 5. And then here, we will have negative 3, since we're multiplying negative 3 times 1. Then we're going to do negative 3 times negative 2 for this one. So that's going to give us positive 6, and then we're adding it to the one below, so we're going to have a 7. And then we're doing negative 3 times 5, which is what we wanted, 15 minus 15, 0. And now Blankinship's method tells us that that entry is the GCD, and the x and y that we want are the 1 and the minus 2. And so let's check. So we have that, in this case, a was 35 times 1 plus the 15 times the y, which is the minus 2, is equal to 5. Of course, we could have done this without doing any of these computations. But the next example will be more complicated, and this is just to get familiar with the process. But why does this method work? What is happening when we are applying this? And it turns out that the way we went about finding this, over here it seemed like I was eyeballing it, but there's really a process. It's just the division theorem being used with this matrix property. So let's do this again. But now let's go from the division theorem. So by the division theorem, if we apply it to 35 and 15, we know that there must be a q and then a remainder. But when we divide 35 by 15, the remainder is going to be, so we're going to have 15 times 2, and then the remainder is going to be 5. And notice that what we did here was multiply by negative 2. And then we apply, so I'm really just doing the Euclidean algorithm. The next step in the Euclidean algorithm would be to take 15, take the 5, and then multiply. And then what we will see is, okay, well 15, well that's 5 times 3, so we have 5 times 3, and then plus 0. And so this is the last quantity before the non-zero entry in the Euclidean algorithm, so that is the GCD. But notice that the entry we multiplied was by the negative 3. And so that's really what's happening behind Blankinship's method, and why it works is that we are applying the Euclidean algorithm in this process. But it's designed so that we get back the x and y that we desire to get the integers appearing in Bézout's lemma. So let's try another more complicated example. Let's try the 55,095, and let me actually bring back the Euclidean algorithm for that. Okay, so I brought back the example that we did earlier when we talked about the Euclidean algorithm. The numbers that we are looking at, 55,095 and 13,755, they already occurred as part of our concrete example in the Euclidean algorithm. So let's go ahead and apply Blankinship's method to this. So here, the first step would be to construct our matrix M. So we have 1, 0, 0, 1, and then we have 55,000, 095, 13,755. And let's take inspiration from what we just did with the previous example. In the previous example, we saw that the negative 2 and the negative 3 were corresponding to the corresponding steps when we applied the Euclidean algorithm. So with that in mind, we see that the entry for the q was 4, 183, 2, and 2. So let's go ahead and do negative multiples in alternation of those. So what do I mean by that? In the same way that in this example, we multiplied by row 2 by negative 2, we're going to start off with row 2 and multiply by the negative of negative 4. So we're going to do negative 4, row 2, plus our 1, and then replace row 1. And so once you do this computation, what you're going to get is that this is going to be, of course, the first entries are automatic. This is 1 minus 4. We have 0, 1. Row 2 is not changing, so I'm going to just recopy the 13,755. But then the entry for the upper right is going to be 75. And so we see that that is just going to be that remainder. And that comes as no surprise. Because what is it that we are doing? We're doing the reverse. We're multiplying 4 to row 2. So we're multiplying this by negative 4. So let's see what we just did. What is happening? We multiply negative 4 times 13,755, and then we're adding it to 55,095. But what we are really doing is just bringing this over to the left-hand side. So we're getting back 75. And that's really the key to Blankinship's method. So we have 75 there. The next step, we're now going to multiply, but to row 1, negative 183. So we'll do negative 183 times row 1, add it to row 2, and replace row 2. Now, this will yield the following matrix, where the 1 minus 4 stays the same, so this is the 75, but then we have minus 183 for the lower left entry. The middle lower entry will be 733, and then by the same logic we just used to realize that that was going to be 75, this entry would be 30. And so we have 30 there. For the next step, we now look at the next one. So here's minus 2. It's going to alternate. So now we're going to multiply negative 2 to row 2. Add it to row 1. Replace row 1. And now that will yield the following matrix. 367, negative 183 in the lower left, negative 1470, 733, and then we'll have the 15 over here, and then the 30 stays the same, of course. So we have that. And then finally, we do one more step, and this will also be minus 2. We alternate, so now this will be minus 2 times row 1, added to row 2, replace row 2. And so now this here leaves the first row stays the same. And then the lower left will be negative 917, 3673, and then of course 0. And now Blankinship's method tells us that the x and y that we are looking for are 367, negative 1470, and so what we have is that if we do, I'm just going to write a times 367 plus b, which is 13,755, times negative 1470, that this here is in fact equal to 15. And so you can now go ahead, verify that computation, and we have now applied Blankinship's method. And now we have a constructive method for finding the x and y in Bézout's lemma. So next lesson, we will be talking about Euclid's lemma, which will be proven using Bézout's lemma. And with that, that will be the last major result we need before proving the fundamental theorem of arithmetic, which we will do on Wednesday. And next lesson, we will also be discussing Diophantine equations, which I alluded to at the start of this lesson. And with that, we will be able to talk about some of the motivational questions that we will be investigating in this course, since so far we've mentioned Fermat's name and then the sum of squares result. But we're going to talk on more avenues that we're going to be looking at on Monday.